Welcome to a new topic in advanced statistics, the one on Poisson distribution. We looked previously at patterns in data. When I know that an experiment follows certain conditions, how can I predict probabilities using a theoretical model? So we studied so far binomial distribution and the geometric distribution, these being the two discrete distributions that we know by now. Please pause the movie and read the conditions under which an experiment is binomial and geometric. After we decide if it's one of these two, we can use a formula to calculate probabilities of events occurring. On the next slide, we are going to look at a new distribution, a new pattern in data, which is called the Poisson distribution. So, for today, we are going to look at how to calculate probabilities on a Poisson distribution and how to adjust the parameter of a Poisson distribution when the interval changes. We are going to look later at the mean and variance in such a distribution. Now I want you to stop this slide and try to match the distribution with the description. Of course, you know the description for these two distributions, so the third one will be left for Poisson. So please pause the movie and think how to match them. Of course, and well done. The binomial distribution describes the number of successes within a fixed interval of trials. So the number of trials is fixed. We took the example with a number of marbles in a bag and drawing marbles without replacing them. And that's binomial distribution. We calculate probabilities of successes, probabilities of having 0 success, 1, and so on. Geometric distribution is number of trials until the first success. And the Poisson distribution will measure the number of successes within a given interval of time or space. Such as, if I watch over my window every day at the same time for 30 seconds, and I count the number of red cars, what's the probability of seeing 0 cars, 1 car, 2 red cars, 2 red cars, and so on? So that's a given. In this case, it's a given time interval. I look for 30 seconds intervals. Another example will be a typist typing on a computer a text. How many mistakes does a typist make per page, for example? The space, the page is fixed per one page. She can make 0 errors, 1, 2, 3, 4, and so on. What's the probability of making 0 errors, 1 error, 2 errors, 3 errors, and so forth? So, as you see, she can make infinitely many errors, right? Theoretically, it's not, practically, it's not possible, but theoretically, I can think of this distribution in this way. So, Poisson distribution measures the number of successes within a fixed interval of time or space. Now, each of these distributions that we studied has a formula that helps me calculate probabilities. Whereas we proved the formula for the binomial and geometric distribution, the formula for the Poisson distribution to prove it's very difficult beyond your course. Therefore, we need to take it as granted. If x is a variable distributed following a Poisson distribution, this has a single parameter, lambda. Lambda is the mean of occurrences. We're going to look later at this. For example, if the typist makes as an average 3 errors per page, the distribution is Poisson of 3. And probability of seeing so many errors per page, x equals 0, 1, 2, and so on, is given by this formula, where lambda is a parameter of the distribution, and e, it's an irrational number that we're going to talk about in the pure math course. And for now, we use the button on our calculator to compute it. So let's look at exercise 1. If x is Poisson of 2, find probability of x equals 1. I apply the formula, so it's e to the power of negative 2, lambda is 2, times 2 to the power of 1 over 1 factorial. So it's 2e to the power of minus 2, which I'm going to put in my calculator to give me 0.270671, which is 0.271 to 3 significant figures. Now pause the movie and try yourself the next two questions. Here are the answers. Now what happens when we have a question that is described like this? Let's pause and read question 7. Thank you for reading it. We always start modeling the question in mathematical language. A number of phone calls arriving in an office switchboard in a 5-minute period might be modeled by a Poisson distribution with a parameter 3.2. So let x be the number of phone calls in 5 minutes. You always need to describe the distribution. Then x is Poisson of 3.2. Find the probability that in a 5-minute period, exactly 2 calls are received. So, probability of x being 2. Using the formula that is in your formula booklet, is e to the power of minus 3.2 times 3.2 squared over 2 factorial. Which gives me 0.209 to 3 significant figures. Next question is very interesting. Probability then more than 2 calls are received. Well, how am I going to do this? That's a cumulative probability. How many calls can she receive? So what values can take x? X can be 0 calls, 1 call, 2 calls, 3 calls, 4 calls, 5 calls. Theoretically, she can get infinitely many calls. We know that all these probabilities add up to 1. So if I want to see what's probability of x bigger than 2, so I want to add all this, then from all of them together, which probability is 1, I need to subtract probability of x being 0, probability of x being 1, and probability of x being 2. And that is going to be my answer. Now for each of them, I'm going to write a formula. So e to the power of minus 3.2 times 3.2 to the power of 0 over 0 factorial. E to the power of minus 3.2 times 3.2 to the power of 1 over 1 factorial. And the third one, and I let you some time to complete the computations. So the answer that I get is 0.620 to 3 significant figures. Now my last example is similar to the first one. Pause the movie and read it. So in a 5-minute period, the number of phone calls, same situation, so let x be the number of phone calls in 5 minutes. And we know that x is Poisson of 1.4. Now, this 1.4, in fact, is the mean of the phone calls. The question is interesting because they asked me the probability of what happened in 10-minute period. Therefore, I will call another variable y, which is the number of phone calls in 10 minutes. Now, y will be itself Poisson of 2.8. If I have 1.4 phone calls as an average in 5 minutes, in 10 minutes I'm going to have 2.8, double. So therefore, question asks probability of y being 2. So it's e to the power of minus 2.8 times 2.8 squared over 2 factorial. And second question asks me probability of y being more than 2. So I will let you try yourself. These are my answers. So please pay attention and think of what happened when the interval, the time or space interval, for example, doubles, the parameter doubles. If it's 3 times as much, it will triple. If it's half, the parameter will half.